Welcome back, AP Stats students. We are now moving into Chapter 12, which is all about sample surveys. So we're incorporating this idea of randomness into how do we go about collecting the data via sampling techniques. So again, your homework as always, read the chapter. It's really important that you guys keep up with the reading of the chapter because there's always things in the book that I can't incorporate completely in my notes. The problems are listed below. And really the objective for this chapter is to identify appropriate methods for collecting data. So just a little background. I'm certain you've learned ways to display and summarize data. There's bar charts, pie charts, we have mean, median, mode. You know the drill. Both those concepts were presented in simplistic methodology and are limited to examining the particular collection of data extent. To make some decisions, we need to go beyond the data in front of us and consider much larger world of interest, so the whole population, as opposed to just our specific people that we can ask questions to. So we will consider three major ideas that will allow us to make this stretch. Idea number one, sampling. So with sampling, the idea is examine a part of the whole. And if that starts thinking fractions or probability, you're on the right track. So the first idea is to draw a sample, and that's what this chapter is about. This is a simple, but most assuredly not easy. We'd like to know about an entire population of data values, but examining all of them is usually impractical, if not impossible. Just think this year, 2020, how difficult a census was to take place, asking everyone involved. So we settle for examining a smaller group or a subset of data values, which we call a sample, and selected from a population. So you apply sampling when you take a small taste of a sausage at Costco and infer that all the sausages will taste that good. So examining a part of a whole, this first idea, I want you to think, opinion polls are examples of sample surveys. They're designed to ask questions of a small group of people in the hope of learning something about the entire population. I mean, you see car companies advertise J.D. Power and Associates #1 ranking. I'm sure like you weren't asked the question, but you've heard those. And professional pollsters work very hard to ensure that the sample taken is representative of the population. If a sample is not truly representative of the entire population, that sample can give misleading information about the population. In the early days of computing, that was known as garbage in, garbage out, or GIGO for short. We want to avoid this misleading statistics. And this is the idea that goes along with statistics, is removing bias. So sampling that is not representative of the population, which either tends to over or underemphasize some characteristic or quality of the population, is said to be biased. And statistics biased means something specifically. It doesn't mean we're against something, which in our colloquial terms is misused. So I want you to think statistically. Biased simply means the sample is not representative of the population. Bias is the Simon Legree, pictured here, of statistics, the one thing statisticians work very hard to avoid. There is usually no way to fix a biased sample and no way to salvage useful information. Get it? This is their garbage in, garbage out. If a sample is biased, there's no use in using it because the data is useless. The best way to avoid bias is to select individuals for inclusion in the sample at random. And that's why we have focused so much on this idea of randomization. So with randomization, the second idea, randomize the selection of a sample. Randomization can protect you against factors that you know are in the data. Randomization can also help protect against factors of which you are blissfully unaware. Think, those are your lurking or confounding variables that we talked about before. Randomization kind of puts them all in the mix and goes, even if I didn't know what was going to happen, we can account for those. Randomizing protects us from the influences of all of the features of our population, even ones that we may not have thought about. And randomizing makes sure that, as much as possible, the sample looks like the rest of the population. A poquito papilito. So not only does randomizing protect us from bias, it actually makes it possible for us to draw inferences. And that's all chapter 6 and 7 and a little bit of chapter 5. Sorry, unit 6, unit 7, and unit 5 about the population when we see only a sample. Those inferential statistics. Now, caution. Inferring from a sample is only made possible when we are careful to choose data values randomly. And you're going to keep seeing this word, randomly, with appropriate techniques. If randomness is not built in to the way we collect data, it is largely useless. Idea number 3, size matters. And it is the size of the sample specifically that matters. So how large a random sample do we need for the sample to be reasonably representative of the population? It is the size of the sample, not the size of the population, that makes the difference. You'll be surprised at how many people you actually have to ask. Now, there is an exception. So if the population is small enough, let's say a small town in Michigan, and the sample is more than 10% of the whole population, the population size can matter. So there is this little caveat. So the fraction of the population that you've sampled doesn't matter. It's the sample size that's important. This idea of collecting and randomizing, it's getting the soup just right. So suppose you're making chili for a chili cook-off, or a soup. If you use too small a spoon to check the flavor, you'll not get a good taste of the chili in the mix. If you use too large of a spoon to check the flavor, you'll not have enough left to enter the judging because you ate too much of it. So you need a spoon that's just right. It does not matter how large the chili pot is, however, just how large the spoon is for sampling. So I want you to watch this PBS little clip, and we're going to come right back to finish the notes for part 1.
Sampling is a familiar idea. To see if the soup is right, you taste a teaspoon, not the whole pot. To test your blood at the doctor, they typically draw less than an ounce. They don't drain you dry. But in many circumstances, finding a representative sample is harder than it sounds.
Let's suppose that this is the population of about 1,000 people in a city. And we want to know, are people for or against converting a park into a dog park? And so these green beads down here are going to represent people who are for it, and the red beads are folks who are against it.
Talithia's first step is to take advantage of an unlikely ally in sampling: randomness.
The beauty of randomization is that as long as you throw everything from your population into one pot and randomly pull it out, you can be sure that you're within a certain percentage points of the actual value that's in that pot.
So the plan is to randomly sample the beads. But how many? That depends on how much accuracy Talithia wants. One measure is the margin of error, the maximum amount the result from the sample can be expected to differ from that of the whole population. It's the plus or minus figure, often a percentage, you see in the fine print in polls. But there's also confidence level. Inherently, there is uncertainty that any sample really represents a whole population. The confidence level tells you how sure you can be about your result. A 90% confidence level means, on average, if you ran your poll or sample 100 times, 90 of those times it would be accurate, within the margin of error. Talithia knows the total number of beads is 1,000, and she's settled on a plus or minus 5% margin of error at a 90% confidence level. That means she needs a sample size of at least 214 beads.
Here are the results. We got 103 red beads and 111 green. So about 48% of our population would vote against, and about 52% would vote for. Now, remember that margin of error that we talked about, that plus or minus 5%? So once you take that into account, those numbers really aren't that different at all. So I guess you could say this puppy is too close to call.
In fact, within the margin of error, the stats got it right. There were an equal number of red and green beads in the jar. While the sampling error built in from the mathematics can be quantified, there are other errors that can't.
The other parts of the error, how we word our questions, how the respondents feel that day, the responsibility to predict what their behavior is going to be somewhere down the line. All those sources of error are something that we can't calculate.
And there's a catch to random sampling for polls, too. A few decades back, when just about every household had a landline, finding a random sample meant randomly dialing phone numbers.
Into the 1970s and the 1980s, we were getting 90% response rates. If we randomly chose a phone number, somebody on the other end of that phone would pick it up and would do the interview with us.
Those days are over. Thanks to caller ID and answering machines, people often don't answer their landlines anymore, if they even have one. Response rates are way down.
Only about 10% of people respond.
So you may be asking yourself, if we're so worried about how many people we should collect, why don't we just ask everyone? And does a census make sense? So, I mean, that's the idea of asking everyone. If we're worried about all of the students' opinions at DC, all I just have to do is ask 893 students for their opinion. So why bother determining the right sample size? Wouldn't it be better to just include everyone and sample the entire population? So we can do that. Those are called censuses, but they're virtually impossible to accomplish for most populations of any interest. By the time you get to the end, the beginning has changed. So how do you get to everyone? It can be difficult to impossible to complete a census. Again, look at what's happening in our country this year. There will nearly always be some data values that are hard or expensive to locate or difficult to measure. And literally, how much time do you got? The census needs to be done in an entire year for the United States population. But if we are given more time, then obviously things are going to change. So before we go into the nitty-gritty details, and we're just going to keep this relatively short, models use mathematics to represent reality. You'll hear me say this. Math is everything. Everything is math. They're interconnected. We are going to talk about parameters, and parameters are the key numbers in those models. Let's get the highlighter. Parameters are the key numbers in those models. Think mean, standard deviations. We've seen those before. A population that is part of a model, a parameter that is part of a model for a population is called a population parameter. We use data to estimate population parameters. A summary found from data is a statistic. The statistics that estimate population parameters are called sample statistics. So how do we separate population parameters from sample statistics? Well, we've seen these before. So let's just talk about the names and how we separate. Remember, if we're talking about a population, we use Greek letters. If we're talking about sample statistics, we're talking about these Latin letters. So Y bar for mean versus mu for mean. S for standard deviation versus sigma. R for correlation coefficient versus rho for correlation coefficient. B for our slope or our regression. Beta for our population parameter regression. P hat for a proportion. And P for our population parameter for our proportion. These last two we haven't seen yet, but we will get there. So the best way to go about randomly sampling is a simple random sample. I mean, it makes sense. Your book uses SRS for simple random samples. I personally discourage the use of the acronym. I want you to write it out because it gives it meaning when you write things out clearly. Our goal is to ensure that statistics we compute from a sample accurately reflect the corresponding population parameters. A sample that accurately represents the population from which the sample was drawn is said to be representative. That is our goal in everything we do, to be representative. Random samples guarantee that each individual in the population has an equal chance of being included in the sample. It is also necessary that every possible sample of the size we plan to draw has an equal chance of being the sample selected. So in addition, Each value with truly random sampling, each combination of values, the sample, has an equal chance of being selected. And this method is called the simple random sample, or SRS as the book uses. A simple random sample is the gold standard. This is the Lamborghini against which we measure other sampling methods on which the theory of working with sampled data is based. So with a simple random sample, different samples drawn at random from the same sampling frame generally differ from one another, which is what we would expect. Each draw of random numbers selects different data from our sample, just like we saw with our randomization. These differences lead to different values for the variables we measure, e.g. the means. We call these sample-to-sample differences sampling variability or sampling error. I want you to think variability, last time we saw that, was r squared, and sampling error was s sub e, or how off our model was from our actual data values. It is this sampling variability that is the basis for statistics. Sampling variability is an extremely important concept. Get it straight in your head. So the differences from sample to sample is the idea of sampling variability, the change between measure to measure. Other random samples, and this is where we're going to pause the video here because it's already been enough information. Simple random sampling does have some shortcomings, however. And actually, the attempt to truly select randomly brings a lot of difficulties. Fortunately, simple random sampling is not the only fair way to sample. So all statistical sampling designs have in common the idea that chance, rather than human choice, is used to select the sample. Thus, there is an element of randomness in every method. If there is not this element of randomness in your method, you're doing something wrong. So designs are used to sample from large populations are often more complicated than just a simple random sample. These other techniques of random sampling are designed to overcome problems of which the statistician is aware of. So we're going to pause here. Our next video is going to go through the other sampling techniques, and then we're going to finish up our series in chapter 12 on sampling techniques on what are bad ways of sampling. So these 3 units or videos should really walk you through all of the foundational pieces of how to do a sampling technique and randomize, but it's up to you guys to really be able to implement these. So all of the situations you need to put into context how you are going to select people to accurately and randomly select them. So I'll see you in the next one, Falcons.